Gravity wants to crush the universe into nothing. So how do stars survive collapse, even after they die? The answer isn't fusion. It's a weird quantum force that says two particles cannot share the same space. This is how quantum physics holds stars up against gravity. Inside every star, a battle rages. Gravity pulls inward, trying to collapse the star. Fusion pushes outward, supporting it. But when fuel runs out, fusion stops. Gravity should win, yet it does not, because electrons have a secret rule. Electrons are fermions, and fermions play by a rule called the Pauli exclusion principle. No two electrons can sit in the same quantum state. Not ever. Imagine a theater where every seat is a sign. When front seats fill, people are forced into higher rows. The crowded audience creates pressure. In stars, this crowding pressure is real. It's called electron degeneracy pressure, described by Fermi-Dirac statistics. And it literally holds up a star against gravity. When a sun-like star dies, it shrinks into a white dwarf, a dense Earth-sized star supported purely by electron pressure. But if the star is too massive, electron pressure can't hold it anymore. The breaking point is 144 times the sun's mass, the Chandrasekhar limit. Beyond this, electrons get crushed into protons, forming neutrons. The star collapses into a neutron star. If even neutron pressure fails, gravity wins completely, and a black hole is born. Space bends, time stretches, physics hits game over. Stars die, but quantum physics fights to keep them alive. That's why the universe has white dwarfs, neutron stars, and black holes. Thanks for watching.